Simple blockchain cryptography. Hello, welcome back. We'll be looking at the simple cryptography and data types, so we will not be looking at in this particular lecture in like advanced zero knowledge proofs or so, but the basic building blocks that we need to run a blockchain. And these are quite simple, surprisingly. It's the mix of different ingredients that really makes a nice cake. It's not necessarily the complex underlying structures that are necessary to build something very beautiful. So the first thing that we'll be looking at are cryptographic hash functions. These are, for example, SHA-256 or RIPE-MD 160. And the underlying idea is you take some arbitrary long input data and you create a fingerprint or fixed size hash, as the technical term is, or digest. And these are this is fundamental. It's a fundamental piece for any blockchain out there to have a secure hash function. So cryptographic hash functions, they take any byte sequence as an input, they produce a fixed size output, and they're typically efficiently computable. So I can recommend you to have a check at this particular website if you want to just play around with hash functions. So from a security perspective, there are quite a few properties that hash functions may exhibit or may not exhibit, depending on which ones you're looking at. Notable ones are collision resistance, second preimage resistance, preimage, hiding, and puzzle friendliness. Puzzle friendliness in particular is quite important for proof of work blockchains, as we will see in the dedicated proof of work lecture. So what do all these security properties really mean? So let's go through them one by one. So pre-image resistance. So in that security property, so for any given h, right, in the input space of the hash function, it is hard to find x such that h, so the hash of the value x, equals to h, right? So if you have an output, right, this output h here, it should be hard to find an x which actually creates which yields that h from the hash function, right? This is pre-image. This is the so-called pre-image resistance. So the second pre-image resistance, so for any given message x, it is hard to find y such that you have two different elements, right? You have x, and x is different from y. And the hash of x equals to the hash of y. So that's the second pre-image resistance. So here it's kind of interesting to see you have a given message x, right? And you want to find another value y, and this should be really hard. Here in the pre-image resistance, you don't have any condition, right? You just have a value x such that you want to find h. So second pre-image resistance, it's a bit harder probably for an adversary because you have an additional condition that you have to meet. And then we have collision resistance. So it is hard to find a pair of values. So we again have an x value and a y value, and they're different from each other. So it's hard to find such a pair of values such that h of x equals to h of y, right? All right. So these are the first three different properties that we're looking at. The other two are hiding. So a hash function h is hiding when a secret value r is chosen from high min entropy probability distribution. So then given h, r given x, it is hard to find x. Okay, this is when kind of the value r here allows you to hide the input x, right? So I mean, it could be that you want to compute the hash of a list of passwords, right? So for example, the hash of the password 123 will be some value, I don't know, let's say a, right? And then if you want to hide, so if you construct a word list, and it's also called a rainbow table, of all the hashes of all the easy passwords, right, then you will have a list of these hashes. If you want to hide this particular, if you want to add some salt, then you can, for example, add a hiding factor and append the value 123, and then the hash will no longer be a but some other value a prime, right? So R in this sense allows you to hide the input 1 to 3. That's the hiding property. All right, puzzle friendliness. So a hash function h is a puzzle friendly if for every n input output n bit output value h, if k is chosen from a distribution with high min entropy, then it is infeasible to find x such that the hash of k concatenated with x is h in time significantly less than 2 to the power of n. So this basically just means, and in simple terms, that brute force is the simplest method to find this particular x here. Okay, so there should be, it's basically infeasible to find it faster than 2 to the power of n. So this means you have to perform brute force, right? Because 2 to the power of n here is an n-bit output space of the hash function. So there's no other algorithm that is known to be better than actually performing brute force. If you have an algorithm that's better, then you might have an advantage in mining. In particular, if you use such a hash function which is not puzzle friendly. So puzzle friendliness is very important, as we see later in the mining lecture. So a search puzzle. So let's look here as a search puzzle. So let's say we have a hash function h, and we have a value id chosen from a high min entropy distribution, and a target set y. Right? So a solution to the puzzle is a value x such that the hash of id concatenated with x equals or is in the target set of y. Right? We want y to be a target set. This is a very typical search puzzle, and we will see later the parallels to mining as well. Okay, very good. Second data types that we're looking at are Merkle trees, and these actually build up on hashes quite heavily. So in a sense, it's really simple. So if you have a transaction here and you want to build a Merkle tree, you take the hash of that transaction, you hash it up, then you take the hash of the concatenation of these two hashes, and you continue doing so until you reach to the top, and this is referred to as the Merkle root. So such a Merkle tree is very heavily used for example, lightweight clients, as we'll see at the end of lecture 1. It is used for any kind of attestation and performance improvements in distributed ledgers in general. So this is really a very important data structure that I can recommend you to look into more deeply, or like think about it more deeply. So finally, the third data type that we're looking at now are elliptic curve digital signature algorithms. I mean, we'll be not really looking into the details of how this works, but for example, the SEC P256K1 curve is quite heavily used in Bitcoin. It's used to sign transactions. So if you have a private key, you're signing a transaction with your private key such that other people can verify that the signature is correct. Given your public key, you can verify the signature then to accept the transaction. And what's however important, that the CDSA is really just used for signature. It's not used to encrypt any data. There's nothing in Bitcoin, at least, that's encrypted. In Ethereum, maybe the network layer might be encrypted, but in Bitcoin, everything is in plain. Everything is publicly readable, whether that's the blockchain or the network layer. There's nothing encrypted. Thank you very much for watching. See you in the next lecture.